Sup nerds. Today I want to talk about difference equations, which are similar to differential equations and have lots of applications in the real world. So first let's compare differential equations versus difference equations. Differential equations, we usually have a derivative equal to some function of x and the function itself. And difference equations, we have what we would call a recursion relation. So something that tells us the next step, y sub n plus 1, in terms of maybe n in the previous step, so some function of n and y. And our solutions for differential equations are functions that are differentiable, so common functions like e to the x, or some other exponentials, or sine of x, or functions that you might be used to seeing in calculus. Meanwhile, our solutions in difference equations are sequences, because these are discrete, so maybe you're going to have something that looks like 1, 2, 4, 7, 9, or some random sequence. And just take a look at the graphs of difference equations versus differential equations. Differential equations, the graph is differentiable, so it looks like a nice smooth looking function. Difference equations you would graph by just drawing points at certain integers. So a little dot at maybe 0, 1, 2, and so on. Alright, let's jump into an example. So the first example is going to be pretty easy. It's just y sub n plus 1 equals 2 times yn. So this is common in population models or a lot of doubling time things. It's saying the next step is twice the current step. And we could add an initial condition, y naught equals 1, but we'll see later that we could take this away. So whenever you're faced with a difference equation, I suggest computing a lot of values. So y sub 1 is 2 times y naught, and explicitly we just plug in y naught equals 1, and get that y1 equals 2. And then we do the same for y2. y2 is 2 times y1, so it's 2 times 2, which is 4. And then y3 is 2 times 4, which is 8, and so on and so forth. We end up getting yn is just 2 to the n. So, like I said, the initial conditions don't matter too much. We could just say y naught is some initial condition and then solve for yn in terms of y naught, and it looks really similar. It's just y1 equals 2 times y naught, y2 equals 2 times y1, which is 2 times 2 times y naught, so 4 times y naught, and so on and so forth until we get yn equal to 2 to the n times y naught. Now, the same way we looked at equilibrium solutions when we looked at slope fields, you can do the same thing with difference equations. In this case, the only sequence that will double each time and is also constant is the constant solution yn equals 0. And you could always solve for the difference equations by saying yn and yn plus 1 are the same, so maybe plug in the same variable for both of them. So if we put x in for both yn and yn plus 1 in our difference equation and then solve for x, we get what our equilibrium solution has to be. As always, if there's anything that you're a little bit unclear about, I suggest pausing and working through the example slowly, maybe watching it a little bit slower. Be sure to understand before you move on to the next one. Alright, so let's do this next example. So it's very similar to the first one. This time we have y sub n plus 1 is equal to k yn. So instead of just doubling each iteration, it's being multiplied by k each time. And so we could solve for the general formula for y sub n, not too difficultly. So y sub 1 equals k times y naught, and then y2 is k times y1, so it's just k times y naught, so it's k squared times y naught. And then y3 will be k cubed times y naught, and so on and so forth until yn is k to the n times y naught. So this agrees with what we had before, where k was 2, which is great. And solving for equilibrium solutions, we should get the same thing as last time. So if we have x equals kx, then we'll see that x has to be 0 in order to have an equilibrium solution. And so yn has to be 0. Now if we were to graph what the solution looks like, if k is positive, it'll look like 2 to the n or like some exponential. So it's increasing by some constant factor each time. If k is negative, then it's going to alternate between positive and negative values. So when k is less than -1, then it's going to be getting bigger and bigger and flipping signs each time. But if the absolute value of k is less than 1, then as n gets really, really big, we could take the limit and see that k to the n goes to 0. So no matter what our initial conditions are, this sequence will go towards 0. Again, if you need to review why this would happen, just pause the video and think about what happens as n gets really big. Now let's move on to our third example. This is similar to the previous two, but this time we're going to add an extra term. So here we have y sub n plus 1 equals k yn plus b. So solving for the general equation is a little bit harder this time. So we have y1 is k times y naught plus b. And then when we plug this in for the equation for y2, we get 3 terms. And when we plug this in for y3, we get 4 terms. And then we start to see a pattern. I suggest maybe doing more values of n if you don't see why it should follow this pattern. But we have a general pattern where y sub n is equal to k to the n times the initial value plus, and then it's a decreasing power of k times b each time. And so we could simplify this by factoring out a b and then using a formula for the geometric sum, so that we get y sub n is equal to k to the n times y naught, k to the n times y naught plus b times k to the n minus 1 over k minus 1. So this is a nice closed form formula for y sub n. Now let's check what the equilibrium solutions are. If we just plug in x for y sub n and y sub n plus 1, and do a little bit of algebra, we get that x equals b over 1 minus k. And we could check that this is an equilibrium solution by plugging this in for y sub n, and we would get that y sub n plus 1 is equal to k times b over 1 minus k plus b. And then after a little bit of algebra, we'll see that this is exactly b over 1 minus k. And that's what it means to be an equilibrium solution. It just means that y sub n plus 1 is equal to y sub n. Again, let's look at what happens when n gets really big. So as n goes to infinity, if the absolute value of k is less than 1, then our first term is going to go to 0, because it's similar to the last time where it doesn't matter what the initial conditions are, we have k to the n times y naught is going to go to 0. And then for the second term, the k to the n is going to go to 0, and we'll just be left with b times -1 over k minus 1. And this is exactly equal to our equilibrium solution, b over 1 minus k. So if the absolute value of k is less than 1, no matter what the starting point is, the sequence is going to converge towards our equilibrium solution. Alright, now let's use this to do a real life example. Let's say we take out an $8,000 loan and the interest compounds monthly. And interest, so at the end of each month, is 0.25% of what the current amount is. So each month you could think of it as multiplying by 1.0025. And say we want to pay it off in 10 years. Okay, so let's set this up. We have y sub n is equal to the amount that we owe after n months, and the initial amount that we owe is just 8,000. We want to pay it off in 10 years, which is 120 months, so we want y sub 120 to be equal to 0. And so our monthly payments, let's call that b, because that's the amount that we're contributing each month. And so and our difference equation says that y sub n plus 1 is equal to our interest times y sub n plus b, which is our monthly payment. So if we plug this into our general equation for y sub n, we get that it's equal to our interest raised to the n times our principal, 8,000, plus b times this geometric factor. And now if we plug in n equals 120, we have y sub 120 is equal to 0, because that's the amount that we'll owe after 120 months. And plugging it into the right side of the equation, we get some expression with the only unknown being b. And we're trying to find which monthly payment allows y sub 120 to be equal to 0. So if we just solve for b, we'll get that our monthly payment is around $77. Now we got a negative value here because we're subtracting away from the amount that we owe. So making a payment of $77 would mean that the amount that we owe is decreasing by that amount. So, as you can imagine, this has lots of real-world applications with anything that generates interest. These difference equations can also be applied towards population models that look discrete. Hope you all enjoyed the video. If you did, make sure to smash that like button and subscribe. And if you have any questions or comments, drop them in the comments below. And until next time.